it's not that I feel compulsive about getting through every one of those transparencies, because we just talked about this before. We'd like to keep this informal. We do want to encourage people to ask questions and have some discussion. And so if we take time, if we digress in this way, it doesn't matter. We don't have to go through all of the transparencies. And one thing I'll also say, as an introductory remark, is that I believe in the subconscious mind as being a good helper for all of us. And because oftentimes the subconscious mind, if you've been working on a problem for a while, you have to have worked on the problem. Then your subconscious mind, while you're asleep or at other times, works on it, and then suddenly you get an insight or a perspective that you didn't have before. And I enjoy that, and I think many of you probably had the experience and enjoy it too. Anyway, last night I woke up at 4 in the morning and I thought to myself, yeah, I must give some historical perspective, because I hadn't planned that beforehand. So anyway, now I have, but of course one could make a whole lecture on it, and that's not my intention. We can be very brief about it. But I think it is useful to have some historical perspective and to realize that it all started with Galvani and Volta in 1790, when Galvani had some frog legs hanging up on a metal hook and noticed the legs twitching and tried to understand what was happening and felt it was something very biological. And Volta, so he published some material about that. He was a professor of anatomy. Volta was a professor of physics. And he disagreed with Galvani about many of the interpretations. And he pursued the idea that it had to do with electrolytes interacting with different electrodes. And of course we know that the voltaic battery and all that follows from that comes from Volta, and nearly all of the, you could say all the electrical excitation of nerve and muscle stems back to Galvani. So, and also you could say that all electrophysiology and all electrochemistry traces back to that time. Then the period from 1850 to 1900, there was apparently a very influential lab in Berlin, Johannes Müller, where he taught many students. And in that time, there was interaction between physics and physiology. And in fact, Helmholtz was one of his students. And the physicists here, I'm sure they know Helmholtz as a physicist who was one of the founders of thermodynamics. And he also, of course, did much of the study on vision of the eye. But he was the first person who made a reliable measurement of conduction velocity in nerve, a classical experiment using the frog nerve muscle preparation. So I don't know whether you people do that in the lab or not, but it's a classic experiment which one can still do, and you can still get a reasonable value for conduction velocity in the frog sciatic nerve. So anyway, there was then, when it comes to cable theory, the first correct insight about that, which is a sort of core conductor, or the German word is Kernleiter, where you have a long tube with conducting material inside and conducting material outside, and the concept that nerves are constructed of these kinds of tubes, and that is the basis for a lot of nerve activity, started with Maciusi, who was a professor of physics in Pisa. But the person who developed it much more was Hermann, who was a student in Berlin, but he had to leave Berlin because he disagreed with his professor, and he ended up in Zurich. But fortunately, in Zurich, he met Weber, who was a good mathematician, and between them, they did a lot of mathematical development on cable theory. And in fact, Weber's work on that is classical applied math for vessel function solution around a cylindrical conductor. And so that's the beginning of core conductor theory, and which was between around 1870. And meanwhile, Kelvin had worked out cable theory, but he actually did it for a practical purpose. The British Telegraph people were laying a cable across the Atlantic Ocean, and Kelvin saved them a lot of money by doing some calculations as to how much conductivity they needed in the copper and how much insulation they needed and so on. And so he developed that theory, but it's interesting to notice that Kelvin's work there depended on the fact that when he was a student, he visited Paris and learned the Fourier mathematics. And Kelvin, he was William Thomson at that time, he became Lord Kelvin later. He was one of the few physicists in Britain that knew the Fourier mathematics, and he made good use of it. Then, around 1880, was Ramon y Cajal began his very important work in neuroanatomy. But in fact, he used the method of Golgi. Golgi had worked out the reduced silver method, which is very similar to photography. You use silver nitrate and manage the solutions very carefully, and then reduce the silver grains to produce images. And of course, the secret of the Golgi method was that for some reason that we still don't understand, one neuron out of 100 would receive the silver deposit and would be stained by the Golgi method. And Ramon y Cajal did this classic work whereby he described the dendritic structure of many, many neurons. And I'm not going to talk much about Sherrington, but Sherrington, of course, did great pioneering work on motor units and the reflex integration, CNS, and last week, several of you heard reference to Sherrington's work. And Keith Lucas did important work on axon's excitability, and he was unfortunate enough to be killed in World War I. And his work was continued by Adrian, and I think some people have told me that they think Hodgkin regards himself as a sort of a successor to Lucas. They were in the same college in Cambridge, and through Adrian and Rushton, Hodgkin followed in the tradition of Lucas. Also, we have Erlanger and Gasser, who in America and the U.S. Did some of the earliest work with cathode ray tubes, and were able to dissect the spectrum of conduction velocities in nerve bundles that have axons of many different sizes. So you have all of that work that went on before 1930. In the 30s, I think there are two important things that you might say that the modern era of neurophysiology begins in the 30s, and there are two reasons. One is that's when electronic instrumentation became available. Although the early ones were pretty crude, and I mean, we've been improving them ever since, but the earliest amplifiers and stimulators that were electronically controlled occurred at that time. But the other important thing was that that's when single fiber preparations began. All the earlier work had been done on nerve bundles, whole mixtures of nerves, where there was never control of which axon was being stimulated. Well, sometimes by careful threshold control, you could stimulate only the most excitable axons, but there's still many problems. So it was at this time when Cole and Hodgkin and Katz worked with single fiber preparations, the squid axon and also the axons of crab and lobster. And Tasaki, following a technique developed by Kato in Japan, worked out the single node of Ranvier preparation. And also Rushton was an important contributor in that period. In fact, Rushton, I believe, was the tutor of Hodgkin when they were doing their early work in cable theory. So they were applying cable theory to understanding of what they were seeing in single fiber preparation. And it was in this period that Cole and Hodgkin made the first measurements of membrane resistivity and membrane capacity. Then we get down to the more recent period, 1946 to 1952, and that was when we began to use intracellular electrodes. See, even this single fiber work was still extracellular. And then the beginning of intracellular electrodes in 1946, that period, was very important in focusing attention on single cells, and also learning much more about the potential across membranes. And there was, in fact, it was Cole and Marmot working at Woods Hole who did the first space clamp, current clamp, and voltage clamp. And as a matter of fact, that was when I was a young apprentice working with them in Woods Hole in 1946. And I made the first axial electrode that they used inside the squid axon. It was around that same time that Hodgkin, Huxley, and Katz were doing their work with squid axons. And they made, although in fact it was, they learned of the voltage clamp approach from Cole, but they knew much better what to do with it. Cole and Marmot didn't have the insight that Hodgkin and Huxley had in separating the sodium and potassium conductances. And from my point of view, there are many different contributions of the Hodgkin, Huxley, and Katz work. But one, there are several. Well, one is that they recognized the importance of distinguishing the potassium currents and the sodium currents, and distinguishing their reversal potentials, and recognizing that the peak of the excited state was dominated by sodium conductance, and that the recovery phase was dominated by potassium conductance. That was a very important insight. Then they incorporated this in their equations and developed a a mathematical model and did the experiments whereby with voltage clamp they could determine all these parameters. And in that sense, it was a very landmark bit of research. And around the same time, Fatt and Katz, who were in close touch, of course, with Hodgkin and Huxley, applied the same kind of approach to the nerve-muscle junction. So you can say that the first really thorough quantitative work on the nerve-muscle junction was done at that time too, in Fatt and Katz using intracellular electrodes in the muscle. And very shortly thereafter, Eccles and his collaborators, and in fact, to go over to the next page then, began to see with the squid axon, it wasn't, it was, most people could understand that it would be possible to have a microelectrode along the axis of the squid axon, but what wasn't known was whether you could get microelectrodes inside smaller cells. And what I summarize here is that the use of very sharp microelectrodes, fine sharp microelectrodes, began in '46. Graham and Gerard at University of Chicago first pioneered it, and Ling and Gerard also in '49. They did the first penetrations of muscle cells and got reliable measurements of the membrane potential. And Nastic and Hodgkin followed on did quantitative study. And Fatt and Katz, of course, did the nerve-muscle junction. So that was all with muscle. Then it was a little later, 52, you see, 52 and 56, where the sharp microelectrodes were first applied to motor neurons in the spinal cord. And the pioneers were Woodbury Patton, and then also Eccles working in New Zealand at that time. And I was in New Zealand at the time that work was going on too. But I worked with Eccles on, prior to the microelectrodes, when we were studying muscle afferent fibers and various other things. When it came to this work, I was so determined to do my own theoretical work that I didn't participate in the microelectrode studies. But when I got back to Bethesda, I was in touch with Frank and Fortis, who were doing similar work with sharp microelectrodes in the cat spinal cord. So all three of these, the last three there, were working with microelectrodes in cat spinal cord, beginning in the 50s and getting on into the 56 and thereabouts. And at that time, there was some data that required some interpretation that I'll talk about in a moment. Now, what I'll say, I don't want to spend any more time on historical perspective, but for those of you who are interested, all these references that I've cited there and some perspective are all collected in the introductory part of a chapter that I wrote for the Handbook of Physiology. It's the 1977 issue, and it's Cellular Volume 1, edited by Ken Dell. And so you can find, if those who are interested in the historical perspective can find more of it there. What I have here is a reminder of what, and once those electrodes were there, we had problems to interpret what's happening. And so this is a diagram. I don't know what this will show up here. This shows a microelectrode in a cell, and displays graphically the concept that this current doesn't flow just across the soma membrane. Much of the current, in fact, majority of the current flows out into the dendritic branches and finally flows out across the cell membrane at some distance. And so what we have to ask ourselves is, well, one of the first important steady state properties is to ask ourselves what is the ratio of the current that flows out through the dendrites and the current that flows out through the soma. And rho was the ratio, the symbol we used to represent that ratio. And values, well, our original tentative values were around 5 or 6. And 5 or 6 times as much current flows out through the dendrites as through the soma. Which means, of course, then, that anybody who was trying to analyze the experimental results, both the steady state results and the transient results, would fall into error if they neglected this large amount of current that was flowing into the dendrites. And what I show here below was, and because of that, there was a misinterpretation of the early transients. And this is actually where I got started in dealing with this problem, because, and here I show what are called the normalized voltage response to a current step, and we consider two limiting cases. Rho equals 0 is the limiting case where there's a soma without any dendrites. In other words, we're saying all the current flows across the soma membrane, the dendrites aren't there, they've been sealed off. The other limiting case is rho equal infinity, which is where the dendrites are dominant and the soma can just be regarded as one point at the end of a long cylinder. And we can then look at the transient that you would predict for those two limiting cases. The case where the rho equals 0, which is a soma without dendrites, is simply a single exponential, 1 minus e to the minus t over tau m. That is the transient that you would predict, and that was the transient that the earliest people assumed they were observing. In other words, if you've got the wrong model, and then you interpret that data with the wrong model, you're going to come out with the wrong time constants, and that's what happened at the beginning. On the other hand, if rho is equal to infinity, you get this steeper transient. Now, sometimes people have wondered, and that's why I've drawn the other curve, why should this initial slope here be steeper? And I point out it's really a consequence of the normalization. What actually happens is if you were to start with the soma and apply a certain current to it, if you then add the dendrites, like for example, if a dendrites with rho equal 5, then the steady state current will be 1/6 as great as that one. And the initial transient here is the same, but it bends over much more rapidly to the lower steady state. Now, if you normalize this curve, you come up to the one which shows the steeper initial slope. But the actual slope for the same current will be the same same slope at the beginning. So anyway, I don't want to dwell any longer. Oh, I will mention that the case when rho equals infinity, the transient is of the form that it's the error function of the square root of t over tau. And then one can, at that time, I think I just computed it by working from the slopes for a value of rho equal 5, one predicts a value somewhere near here. And an article that was published in Science in 1957, it was pointed out that there were reasons to believe that the actual case should be between these two. Yes?
Excuse me, you have two curves with the rho equal to 5. One is normalized, one is not. This is the...
Yeah, this one is not normalized. This is the same current as here, the same amount of current. And the uppermost curve is a normalized version of this. This was just sketched in by hand to show that you get, to understand why it is that if you started initially with the same current and the same cell but added the dendrites, you should see a much lower steady state voltage. And then if you normalize it, you come up with this one. So that was actually the beginning of my theoretical work on motor neurons and interpretations that involve cable theory, because when you have the dendrites with the point soma, what you're doing is emphasizing the cable aspect of the dendrites, and that's what led to correction of the time constants that were being deduced from the data. Now I come to what usually would have been slide 1. Slide 1, I always remind people that when we talk about dendrites, we're not talking about some hypothetical structure. We're talking about a structure like this or this, which represents 95% or more of the surface area of the soma and dendrites. If the soma, you see, in this case, it may be a ratio of 101 surface areas. In the case of motor neurons, it's more like 20 to 1. That is the surface area of the dendrites compared to the surface area of the soma. So that means in any modeling which neglects the dendrites is obviously bound to produce serious errors. One of the points about it is, though, when Ramon Cajal first drew this, he apparently he didn't use camera lucida. He was very skilled. Apparently, people who studied his drawings later realized that he was very accurate. But presumably spent many hours drawing this, and that's one reason why I save you the trouble of trying to sketch it. But the other thing to realize is that this was Cajal when he wanted to discuss circuits. So when he was discussing circuits, he, of course, attenuated the dendrites in this manner and showed several synapses on there, simply for convenience. And also in Laurenti Deneau, who did some very fine anatomy and physiology, he made diagrams like this, showing endings on the soma and showing recurrent collaterals and things like that. Again, well, he showed a little more dendrite, but not much. And in a textbook where Lloyd was discussing these things, he did this sort of thing. And in the famous McCulloch and Pitts modeling, they ended up with a well, I assume that this diagram was derived from that one. And they just had these 3 little cusps, and they show an inhibition with this little circle and show the excitations. And the point I make here is that whenever people drew circuits, they ended up having to do something like this. And before you knew it, the people who hadn't done anatomy themselves forgot that the dendrites were there. And I really think there was a psychological factor there that people, because they didn't draw them, they didn't think they were there. And what this is an intermediate kind of a drawing, which I made some time ago, where I pointed out, well, let's at least show a little bit of the dendrites, and let's ask the question, does it make a difference if we have different synaptic distributions? For example, case A, this doesn't necessarily have to be a single fiber, it could be several afferent fibers, but suppose they have their endings on the distal dendrites. Suppose another afferent has its endings on the soma. And suppose another one actually lets them off in a sequential manner, which, because of time delays, would actually give you a spatiotemporal sequence. And you can ask the question, well, does it make a difference? And I think the anatomists, I think they felt that it made a difference, but they didn't know how to discuss it. And I think this is where cable theory comes in, to try to deal with that sort of question. So then this is a kind of an outline which I could have given first, but I'm giving it to you now, which is to point out that, well, we have this anatomical information about the branching and the fact that synapses are distributed over all these branches. In fact, the synapses may number 10,000 or even 100,000 in case of Purkinje cell. And whereas originally some people might have doubted that there were synapses over all these locations, electron microscopy later on proved, in fact, there are synapses over all of these dendritic surfaces. And in many cases, when the dendrites are spiny, the synapses are in the spines. And various new anatomical methods, for example, HRP has confirmed all that Golgi showed, and in fact, it's more reliable. Sometimes Golgi method will fill most of a cell, but leave 1 or 2 branches unfilled. HRP seems to be more reliable. Also cobalt, I think, are more reliable in filling all the branches. And then there are also some dyes, such as the Lucifer yellow dye. And these have all confirmed what we already suspected, that you do have synapses distributed to all of these dendrites. Then we have the membrane biophysics, which came from the work that I mentioned before on squid axon and earlier work on other axons, where we have a concept of passive membrane, and then we have a concept also of synaptic membrane, which began with the work of Fatt and Katz. And we have a concept of the active membrane, Hodgkin-Huxley membrane. And now, of course, we know about many different kinds of channels. At that time, the channels were unknown at that. I don't know what some of you realize. You now know about many different kinds of channels, but back in the 50s, the channels were unknown. So you have these. What I'm emphasizing now is we have different domains of information: the anatomical, the membrane biophysics, and then the electrophysiological measurements you do with an intracellular microelectrode. And with a microelectrode, you can do 2 kinds of experiments. You can stimulate and record a transient, but you can also record the results of synaptic excitation. And then, in fact, one can also, in other situations, and next time I will be talking something about extracellular fields and how one can try to interpret those in relation to population responses of neurons. But right now we're going to focus on these. But the point, the general point I want to make is, if you have these different kinds of information and you want to deal with them in an integrated way, the only way to do it is with a mathematical model. And so that's what we're concerned with, that we have mathematical models which combine the membrane models with the geometry of the neurons, which have to be dealt with by means of cable models. And in that way, this was originally applied to motor neurons of cat spinal cord, and later on, also to dendritic spines and other things we'll talk about later. I don't know whether it's distracting for you to have these printouts, or whether it's just useful. It certainly saves you scribbling. But yeah, well, we can ignore the bottom half here. The top half is designed to now give the intuitive understanding of what underlies cable theory. And this, in the early work, the electrotonus was done with extracellular electrodes. And if you had a cathode near the surface of the neuron at one place, this is like in a long axon, and an anode here, one of the things that was observed was that you could get an effect at a distance away, and this was because of the current spread. And the early term that the Germans used was electrotonus, and there were various theories, some erroneous theories about that in the early days, but it was Hermann who worked out the core conductor model, and the understanding we have is that the membrane resistance is very high. And therefore, when you apply current, and particularly here, if you apply current with an intracellular electrode, it cannot just go out immediately at the nearby area because the resistance of the membrane is so high that the current spreads for a long distance along the axis before it crosses the membrane. So it really has to do with relative resistances. The resistance to current flow along the axis is less than the resistance to current flow across the membrane. You get a spread. So that's the concept. The mathematics is just then a way of formalizing that. And those of you who looked at the chapter in the book, in the Koch-Segert book, will see this, and I will go over it fairly quickly. But just to make it clear that we have a straightforward way of doing this, we first ask the question, what is the current flow along the axis? And this here, it's I sub I is the current, intracellular current, or some people call it I sub A, axial current. But that current is in fact proportional to the gradient of potential along the axis. So you can do it in terms of old-fashioned physics with the delta V and the delta X, or you can just go right over here and say that the partial derivative of the potential along the interior, V sub I means the intracellular potential. It's assumed to be a function of only one variable, that is the distance along here. And so that partial with respect to X is equal to minus I times Ri being the resistance per unit length of the intracellular core. Sometimes it's called core resistance. And then we can also, if Ri is uniform, if you have a uniform cylinder and you have uniform properties so that Ri, the resistance per unit length, is a constant, then you can make this second derivative and simply say that the second derivative of intracellular voltage with respect to distance is equal to Ri times the first derivative of current with respect to X. And that we can recognize if we look at the next diagram. So you can talk about it even as a one-dimensional Laplacian, if those of you who think in those terms. What we can say is the difference between what flows into a volume and what flows out of the volume, it represents what comes out across the membrane. So we can say that the current density across the membrane can be recognized as being representing that difference, and here we have it in the differential form, that the membrane current density is minus di dx, where we're talking again about the intracellular current. And notice we had the dx up there, so that means there's a equal sign missing here. You can put an equal sign in here. We're saying that the membrane current density is proportional to that second derivative of intracellular voltage with respect to X, and the proportionality constant is 1 over Ri. So that is the first part of the derivation. Now what we've done is we've related the membrane current density to the voltage distribution intracellular. Yes?
Can there be no other source of loss of current, like recombination of ions?
No, I don't think that's realistic, but you could have an electrode in there, and then you definitely have to take that into account. You could also, if you had a local bit of membrane that was active in that it was generating current, then that also would have to be taken into account. But I don't know of any examples of what you're saying, unless you want to generalize what you were saying to change in the membrane properties. But clearly, and in fact in this chapter that I referred you to, the 1977 chapter, I have included a careful discussion of what the effect is if there are electrodes present, and also a discussion of what happens if there's an extracellular gradient that's important too. Here, there's a trick here that by focusing attention on the intracellular voltages and the intracellular gradients, that's where most of the action is. because the extracellular potentials tend usually to be much, much smaller and can be ignored for many purposes. The only time when they can't be ignored is if you take an axon and place it in oil. And that was one of the techniques they used in the old days. In order to get more current to flow into the cell, they'd place the axon in oil so that the extracellular resistance would be just a very thin film of saline, and that would have a high resistance. And that, under those circumstances, then you have to include the extracellular gradients and extracellular voltages as part of the analysis. So we've gotten this far, and then to go any farther, we now have to make an assumption about the membrane. And the standard thing for the passive membrane is which is well established from the work especially of Cole back in the 50s, that you can treat it as having a capacitance and a resistance in parallel. And if that's uniform and passive, we refer to it as Rm, or sometimes the reciprocal GM, that is the conductance per unit length. And they can be related to conductances per unit area too. So if we have that simple model, and we regard then that as being a chain of compartments, if you like, and you can take the limit of case so that you end up with a continuous membrane, then you can say that the current that flows across the membrane, the current density, is going to be equal to the membrane capacity per unit length times the time derivative of the voltage, and also the net difference of potential across the membrane, which here it's VI, that's the intracellular potential, minus VE, that's the extracellular potential, minus the battery, the reversal potential. And you take all those into account and divide that by Rm. That is the expression for the membrane current density for that kind of a simple model. And now all we have to do is equate the expression for IM over here, or IMRM here, and we end up, by equating those, we have the cable equation, which is, well, it's stated here. No need for me to run through it. And you can use a dimension as variables, that cap x is x over lambda, cap t is t over tau, then the cable equation is expressed as here, or is at the bottom of your sheets, I guess. That is the dimensionless version of the cable equation. And furthermore, if we're talking about steady states, of course, the time derivative is 0, and you simply have here the second order ordinary differential equation, which is the one you solve for steady states in the cable. Well, I wasn't sure how much to do about it. I think if one is having several lectures, I mean, rarely do I, in a single lecture, I wouldn't try to cover this, but in a group of 6 lectures, I think it's worth seeing how the cable equation is actually achieved. And unless there are any questions, I want to go on then to the next thing. But I'm quite willing to digress if there are any questions that people want to digress on. The next chart shows the steady state solutions. And it's important to emphasize that there are quite a few different steady state solutions. They're all perfectly valid, and the only difference between them is the boundary conditions. And this is something that many physiologists have overlooked over the years. They think, many physiologists who aren't aware of the importance of the boundary conditions consider only the exponential decay that is an exponential out to, I usually try to avoid the word decay. I use decay for time changes and use spatial decrement for dependence on distance. So what we're talking here is an exponential decrement with distance. And that is the limiting case if you have a cylinder of infinite length. But in fact, we rarely, axons are often sufficiently long that they are as though they were infinite. But oftentimes we're really dealing with finite length. And when we have finite length, then we have to ask ourselves, well, what is the boundary condition? And one kind of boundary condition is to have a sealed end. And well, we can look at the equations in a moment, but in terms of the curves, if you have a sealed end, it means that the voltage gradient, the dV/dx, is 0 at the end. No current leaks out of the sealed end. And that is the boundary condition, which when you apply it to the equations, you get a solution which is usually, the most convenient form usually involves the hyperbolic cosine of L minus x. So that expression is useful. And the reason it's useful is because the sine, which has a non-zero slope at the end, and therefore the coefficient of the sine is 0. what I should say then is that when you have the second order ordinary differential equation, you have the solution which involves two arbitrary constants. It can be either this form here with the simple exponentials, or these alternate forms which are equivalent. The hyperbolic functions are just arrangements of the e to the plus x and e to the minus x. But they happen to be convenient because one of them will give you a zero slope and the other will give you a zero value at one of the boundaries. And that usually means that you can set one of the coefficients to zero. This is what I was getting at here. So when we have a sealed end, we have the condition of the zero slope at the end. And this example, H is the case where you have a sealed end at a distance of 1 lambda from the origin. F here is the case of having sealed end at a distance 2 lambdas away, and J is the case of having a zero slope at only a half a lambda. And you notice that you have less decrement in that case. But all of these cases of the sealed end have less decrement than the infinite, the case of the infinite length. But you can get even steeper decrement for these cases here, and what those cases are is a different boundary condition. That's the case where V, that is the departure of the voltage from its rest value, is clamped to 0. In other words, the membrane is clamped to its resting value in these three cases, A, B, and D. Then I also have two intermediate cases, this one G here and this one C here. Those are neither of the extremes. It's not a zero slope, and it's not. I think in this case, let's see. The ratio of leakage to what it would be for the infinite case is 1/4 in this case, and it's 4 times in this case. What it means is that you can have intermediate boundary conditions, but then you can't reduce the solution to a single term. You then have to consider both terms of the. You have two arbitrary constants that you have to deal with. And then just for the sake of completeness, I decided to include two here where if you actually clamp the voltage at the other end to some other value, you'll get solutions of that kind. And all of these can be expressed mathematically if you just pay attention to the boundary conditions. And what I have there at the bottom then is a general result which is useful when we want to look in a dendritic tree. Because what it says here is that the solution depends upon the ratio of the conductance. By GL, I mean the conductance for leaking out at the far end. If the far end of the cylinder is not sealed, you have some leakage there. GL represents the leakage conductance at the end, and you compare it with G infinity, which is the value you would have if there were an infinite extension of the cylinder. So it's that ratio there, the ratio of the actual leak to what it would be if you just extended the cylinder. That is a very important parameter, and in fact in some of my earlier papers I used a symbol B for that ratio, but I've returned to this because somebody who doesn't know the early development, B doesn't mean anything, it's just a letter. So here we show what the functional meaning of it is.
Can you repeat please, what is the meaning of G infinity? Can you repeat please, the meaning of G infinity?
G infinity is the input conductance of a cylinder extended to infinity. And in fact, you'll get the same value at any point along an infinite cylinder. You just enter an infinite cylinder, and G infinity in one direction will always be the same. In fact, if you're allowing current to flow the other way, then you get the combination of G infinity that way and G infinity this way, which will be in fact twice as great.
And GL is
And GL is when you have the cylinder ending there, but it's leaky, or you may have two branches, and then you have to ask what is the input conductance of the two branches, and they become the GL for that expression.
Answering?
Yes.
Concerning the sealed end, about the sealed end.
Yes.
Well, if you talk about the transient solution, it's difficult for me to see what will happen to the current that gets to the sealed end and starts to maintain there, and the current starts to go to the membrane. What would happen over
Well, in the solution, really no current gets to the sealed end, because no current can leave the sealed end, so it means that the gradient actually reaches 0 as you approach the end. So the problem sort of solves itself in that you simply can't have any current flowing out there. And what it means is that if you have a short cylinder with a sealed end, not so much current can flow into it because it can't go out the end, so it has to go across the membrane. The membrane has a high resistance, so not very much current can go in there. And that's something we'll come back to a little later because it affects the decrements that you get. Well, so this is a general expression that can be used for any cylinder with very different boundary conditions, and it is the basis for an iterative solution in a tree. And in fact, it's used all the time in people who solve dendritic trees on a computer. They're just using this expression over and over again. Now, I debated this. This was something I just produced, but I felt there was well, with time running out, maybe I should skip over it very quickly. And those of you who are really interested can go back over it. Unless you want to slow me down, we can do that too. But what I did here, this was the expression that was at the bottom of the last page. And the thing to realize about it is that if you differentiate with respect to small x, then you will get minus v0 over lambda, because the big X is an x over lambda. So you'll get a lambda in the denominator. Also, the cosh becomes a sinh, and the sinh becomes a cosh, and you get this expression. Now, if you ask what is that slope at x equals 0, and actually I took the minus sign out here, then you'll notice that if x is 0, this is the sinh of L, and that's the cosh of L. And we can divide through the numerator denominator by cosh L, and we get a very simple expression. This becomes a hyperbolic tangent of L. Here we have just this because we divided through by cosh L. And you just make a note, I didn't write it down, but you divide through by cosh L, numerator and denominator, to get this expression. You have a 1 here, and you have this. This, then, is the expression for the slope at x equals 0. Now, the slope at x equals, and then we can take the limiting case. If GL is 0 for the sealed end, of course, GL is 0, then this drops out and that drops out. You simply have the tangent, hyperbolic tangent of L, which is a useful expression for a cylinder with a sealed end. Now, the reason for looking at the slope is because the input conductance is the ratio of the input current to the input voltage. And the input current is simply the gradient at the origin at x equals 0 times divided by the resistance per unit length. So this is an expression for the input current divided by the voltage. If you look up here, you have the voltage in the numerator, so that cancels out. You're left with this expression. Let's see, yeah, the lambda here came from there. The Ri came from here. So you have 1 over lambda Ri, which is the factor here, times the same expression we had in the parentheses here. This is now an expression for input conductance. And there are several ways of looking at it. This factor here really is G infinity, depending on what I mentioned before. And you can see that it would be G infinity because if you go to infinite length, if L is infinite, the hyperbolic tangent becomes 1. So this becomes 1 plus that ratio. Down here, this becomes 1. So you have the numerator and denominator becoming identical. And what is one of several ways of showing that the input conductance for a cylinder of infinite length is this 1 over lambda times Ri. That has sort of an interesting mnemonic too, that the core resistance of a lambda length of the cylinder is exactly equal to the input resistance of an infinite conductance, of an infinite cylinder. And I think in the chapter that some of you looked at in the Hoek-Saget book, I pointed out that there's G infinity can be given several different expressions, one of which is in terms of the surface area, and which we can make use of at a later time. And I don't think I want to waste all of our time to go through all the steps here, but those of you who are interested can look through it later. But what you end up with is that it's equal to the surface area of the cylinder divided by the electrotonic length, that is little l over lambda, times the membrane conductance per unit area. And that is a useful result, which in fact was not included in my earlier papers because I hadn't bothered to work through it, but I've used it more recently because it actually is helpful in getting insight into some of the relations between input conductance and input resistivity. Well, what I have here with this diagram was to try to give some insight into the difference between the limiting case, for example, if you have an isopotential membrane, and such as a spherical stoma, but it doesn't have to be spherical, so long as it doesn't have any extended parts or doesn't have any constrictions, it can be isopotential simply because the resistance to different points in the interior is very low. So when you have that, the input conductance is always very simply, it's simply the membrane conductance per unit area times the area. And people who were neglecting dendrites were assuming that they could just use that kind of formula, and the only question is which area should they use. Now, when you have a cylinder with sealed ends, what I was just telling you was that you have this expression which involves a hyperbolic tangent of L, but then if you go through what I was just saying, you can get that G infinity is actually equal to the area over capital L. If you make use of that fact, you have the relationship that the input conductance is equal to the membrane conductance per unit area times the area times this factor, tangent hyperbolic L over L. And that factor, you can look at it as has some limiting values. If the L is very small, very short, then the tangent hyperbolic L is equal to L, and you simply have 1 here, and you revert back to the expression above. That it's a simple relationship between area and membrane conductivity. But when L is significant, this ratio is less than 1. And that is a correction factor which is due to the fact that the membrane is not uniformly polarized, that there is a decrement with distance, and this is a correction that is involved in relating the input conductance to the membrane conductance per unit area. So this is what we're involved in when we have a neuron with several dendritic trees. Now, if the neuron with several dendritic trees is such that, and I haven't actually gone into this with you yet, but I think most of you have heard about it anyway, that when you have certain branching constraints, an entire tree can be treated as an equivalent cylinder. And then we can say, okay, let's have this neuron composed of many equivalent cylinders. If they all have the same length L, then we have the same expression applying to the whole neuron. That we can say the input conductance of all of these dendrites is simply going to be this product of conductance per unit area times the area of all those dendrites times this ratio, hyperbolic tangent of L over L. And this is strictly true whenever you have the equivalent cylinder assumption. But now we know that in recent years people have done all this anatomy of all these irregularly branching patterns. Yes?
I'm having a little trouble understanding one thing. It seems to me like the input conductance should somehow be related to the ratio between the dendritic resistance and the membrane resistance. And I don't know where that ratio's gone. You see what I'm...
Well, what I'm using here, this is what I derived in the previous page, showing that this membrane resistance here is assumed to be the same over the cylinder. That is the membrane resistance, membrane conductance per unit area that we're assuming that's the same everywhere. And what we're saying is that that times the area doesn't give the answer because you have this additional factor. Now, what is it? I'm not sure what it is you want to know.
Somehow the internal conductance or resistance seems to me like it should...
You want to know where... that isn't lost. You have to remember that capital L is little l over lambda. Little l is the true length, actual length in millimeters or microns. And lambda is something I guess I didn't dwell on before, but in fact it's the ratio, it's a square root of the ratio of Rm over Ri. And so it depends on membrane resistivity and core resistivity. So what you're asking about, it's buried in lambda. Lambda does give that. And so the capital L does include that. And what we're saying is it depends on how long the cylinder is in relation to its value of lambda, which determines how much electrotonic decrement there is, and the amount of electrotonic decrement is what makes this factor be less than 1. And what we're saying is that, okay, if you have a neuron where all the trees are equal cylinders, or they don't have to be equal diameter, but equal length, that is electrotonic length, the L over lambda, that would mean that a thicker cylinder could be a longer actual length, and divided by its lambda could still give the same cap L. They still have the same form, this formula here. Now, the reason for focusing on this for a moment is it's something we've made use of recently, because when we ask if trees are non-ideal and have all different kinds of branching, then we can say, well, what factor do we use instead of this? Yes?
I didn't understand there are two equations where G appears in a little bit different.
Yeah.
The one that in this page is with the tendency topology of L and
You think there's an inconsistency? Well, I hope not. Let's see. Yes?
because in the middle of the last page
Yeah.
you just wrote that G equal G infinity. All the things there in the
G infinity times the hyperbolic. D infinity times the hyperbolic tangent of L. There it is, right there. That's what you have on the other
but
page.
in the former page,
Yes, that's, you see that on the former page too.
no, you have another things like GL divided by G infinity and all.
No, well, no. If GL divided by G infinity is 0, when you have the sealed end, we're talking about sealed end here. So then you come down. Then it reduces to this.
Okay.
And then, as I pointed out before, G infinity can be restated in this way, and that's how you come out with the expression I've been talking about. Yeah, well, it's easy to get lost in these things, which is one reason why I wrote it out. Yes.
Could you give some intuition about lambda? What physically does it really represent?
Oh yeah. Well, I have. Well, for big axons like squid axons, it can be as much as 1 millimeter, and for finer dendrites, it can be more like of the order of 100 microns. You can work it out for any particular values, and I think I do have a transparency further along where I actually give some example values. But that's the kind of ballpark we're talking about. So the final point I wanted to make here, and in fact this has been in the 1992 Physiological Review article, which I give the pages here, we actually present this result, and I presented it once somewhere else. It was of some interest to go back and look at experimental data for non-ideal trees and ask ourselves, what is the value of this ratio when you cannot express it in this way? And the point is that with these computer programs that we now have where you can analyze, you have to assume a value from the membrane conductance, but then you can go through step by step and compute the input conductance for a whole tree of arbitrary branching, find out what that input conductance is, compare it with the membrane surface area and the membrane conductance per unit area that you assumed in the calculation, take that ratio, and that ratio will be some factor, which are called FDGA if you want to. It's a sort of a pun. In America we talk about fudge factors. But anyway, this is a factor less than 1, and it corresponds to this factor for the idealized geometry. And so you can actually say that it implies an effective electrotonic length, even if there isn't an actual one. Or you can ask some questions about how should you assign electrotonic length to an arbitrarily arranged tree. And this is one way of doing it. And so we can say that this is a generalized correction factor for the effective electrotonic decrement in non-ideal trees. And there's in this review article, we look at the data that Burke and Segev and Fleshman obtained for 6 alpha motor neurons of cat spinal cord, and for that case, this factor turned out to be 0.71, and it implied an effective length of 1.16. And it's interesting, in that case, they calculated it another way. They said, let's take every terminal branch and let's just calculate all the little L over lambda values. In other words, the delta X over lambda of each increment out to the tip, and take all those tip values, and for want of a better way, let's just average them all, even though they may not all, maybe they don't deserve equal weight, but we give them equal weight, we average them, and they came out with 1.20, which isn't too, I mean, the two things are rather close. You might say, well, that justifies just averaging the tip values, but what it means is that we have some internal consistency here. We also try to estimate it a different way from transients, and I'll talk about that later. But it is a way, and I've been encouraging, and Burke is looking at other neurons, and since the point about this is that people have sometimes complained to me and say, well, when we look at actual neurons, they're not ideal, you don't have ideal branching, so all that you should throw it all out the window. And my answer is no, you don't have to throw it out the window. You just recognize that there's a factor which corresponds to this factor for the idealized case. And you can ask yourself, well, what is that factor? And my prediction is different types of dendritic trees will have different values for that factor. And I see where I've used up the first hour, and I guess it's time for everybody to have a break. And I have no idea at what point I would reach before the break, but this is probably a good point. So I don't know what do we have, a 10-minute break? Ri is equal to, is proportional to d to the minus 2. The way to understand that is the resistance along the core is related to the cross-sectional area. And the cross-sectional area is proportional to the square of the radius or the square of the diameter. And so that means that the core resistance is related inversely to the square of the diameter. So if you combine those things, you get the 3/2 power. And you can go through it in many different ways, and if you don't make a mistake, you come out with the 3/2 power. And that 3/2 power is what's involved when you match dendritic branches to the parent. If you have two daughter branches whose diameters add up to the 3/2 powers add up to the 3/2 power of the parent branch, that means you have a match. It means the two daughter branches, if they have the right lengths, will actually take the same current that the parent branch would have had if it had been extended. And so the concept behind the tree, which is equivalent to a cylinder, is if you have the condition, and I may have it on one of the next slides, is you have the condition that the d3/2 of the parent branch is equal to the d3/2 of one daughter, let's say, well, the d daughter 1 plus the d3/2 of daughter 2, then you have this matching. And then if the daughter branches, they can have successive branches, but if the final value of L, capital L, is the same for all the different parts of the tree, then the entire tree can be collapsed to equivalent cylinder for some purposes. And I guess there's more detail on that in the chapter, and probably wouldn't be productive to spend more time on it right now. I want to briefly give this example, which John Rinsel and I worked out some years ago. In fact, we did it in steady state in 73. We published the transient solutions in 44, and I mean 74 the next year. And but it was really based on physical intuitive insights, but then we went ahead and did the mathematics to demonstrate it all, and we got the equations. So this, if you have a tree, and these other trees could be represented by their equivalent cylinders, but in this particular, in some diagrams we did that. In this one I showed them all complete, just maybe to make it a little more impressive, that you can have all these trees, they can be extensively branched, but as far as this particular analysis is concerned, each one can be represented by its equivalent cylinder, and only the tree where we're looking at the input do we have to look at the separate branches. And here we designate an input branch and its sister branch, and then here are the first cousin distal terminal branches, and these will be the second cousin branches. And now we can, in a moment I'll show you how we got the solution, but the result of that solution, this is for the steady state, is that you get a very different result if you apply the same current. In one case, you apply it here at this one input branch, where you get these voltages. And the other case, of course, the contrasting case, is if you applied the same current at the soma, you will only get this much depolarization. In fact, the input resistance at the soma is only 1/16 as large as the input resistance at the input site. Another way to put it is that when you're out in distal branches, especially successive orders of branching in the fine diameter, you have a much larger input resistance. And because you have a much larger input resistance, a given amount of current injected is going to give you a much larger voltage change or depolarization. And one of the other points that's really relevant to the work we did later on dendritic spines. In fact, we did these calculations partly because we wanted to prepare ourselves to work with dendritic spines, because we said if you have a synaptic input on a dendritic spine, it can't be on an equivalent cylinder. It's got to be on an individual branch. So here we're talking about input to a branch. And notice this. These two branches, the input branch and the sister branch, are the same length and the same diameter. And look at the difference in the voltage decrement. You have this very steep decrement in the one, you have this very slight decrement in the other. And the reason is because of the boundary condition. This is a sealed end boundary condition. No current can flow out of the end. All of the current has to flow across the membrane, and that means that this branch, if it's short enough, it's almost isopotential. In fact, when we talk of the dendritic spine, which is very short, very fine, we regard it as almost isopotential. Whereas this branch, which is the same length and the same diameter, has a very steep voltage gradient, and it's because it's not a sealed end. It has, in fact, more than an open end. It's not more. I mean, what I mean is, it's the GL over G infinity here is greater than 1, because the parent branch is going to have twice the D3 halves value, plus you have this one. Of course, this one's not taking much current. So the main effect is that the parent branch is taking has twice as much as D3 has value, and successively as you go on, you have more and more of the tree opening up. So I think I once did the calculation. I think maybe, I'm not sure, but I think it's about 5 times. The GL over G infinity is about 5 in this case. So you have all these, and you see here also going even out into these first cousin branches, there's not a very large voltage decrement. You have some here and these. And so this gave us some valuable insights that were related to later on to dendritic spines. And then what I want to go over very quickly and point out that we got the solution by physical intuition by looking at superposition. We knew that superposition, when you have applied currents, superposition does apply in this complicated tree. So this is the first thing, and we're looking at odd and even functions. And what the starting point, I'm going to run through this fairly quickly, but I want to try to get across the idea. We ask ourselves how, well, we contrast an even function here, which means that if we apply half of the current at one end and half of the current at the other end, by symmetry we have a zero slope in the middle, which is also like a half cylinder with an insulated end. So we have this kind of an even function. If we have an odd function, we can get an odd function by putting plus I over 2 here and minus I over 2 at this end. And that's the same as clamping this end to the middle. It means we have a zero value of voltage here and we have this odd symmetry. Now if we combine these two, what we're doing is that this minus a half and this plus a half cancel each other out, and it's like having an insulated end here and having all of the current injected here. So this is the solution for injection at one end and the sealed end at the other. Now, so that's the basic idea. Here, then, we're taking a neuron composed of 6 equivalent dendritic trees, and first we can put I over 6 into every one of them. Then we can take any pair, and we'll see this kind of an even function like that one up there. Now, we put 5 6 plus in one and a minus 1 6 in each of these. The purpose of that is that these minus 1 6 should cancel those plus 1 6. And here, the 5 6 will add to the 1 6. So here, I save you the trouble by giving you these rocks prints of this. You don't have to try to draw it all, but you can concentrate on the thought. The thought then is, if you superimpose these two cases, you now have sealed ends on all of these, and you have all of the current being injected here, and the solution takes this form. And one can work it through mathematically, and that's what you get. Now, the next one shows what happens. So that takes care of the different trees. Now we're going to the branches. And it's the same principle. We say, okay, let's have 2 branches. And first we consider a positive, half of the current positive here and positive there, and we get the solution for that. Now we consider the case of half of the current positive there and negative here. So this is the even function. Here's the odd function, plus here and minus here. And notice that when it's plus here and minus here, it's 0 at the midpoint, so it doesn't affect The rest of these don't know that anything's happening here. This because of the zero here. And that's true for the steady state. It's also true for transients. In fact, it's more interesting, you might say, for transients. That if you have equalization between a plus and minus value out in the tree, it can affect just the distal branches and not the rest of the neuron at all. So then you combine these two, you have input in the one branch. Now you can do it by successive branchings. You end up having the input all in one branch and none in the others. And those of your interests will find the details of this. The steady state, where this was presented, is in Biophysical Journal 1973. And the same ideas were then used to get the transient solutions, and they were published in 74. This is work by John Rinson. So now I'll show you an overview, which I could have used at the beginning, but I remember I showed it to Idan and said, well, you're going to show them this all at the beginning, it'll take too long. But I think maybe at the midpoint, it's useful maybe to say, well, what is it we're trying to cover, and you'll see how are we doing. So we're talking about models of dendrites and synaptic function overview, and I told you at the beginning that we have mathematical models, and we have to combine the dendritic geometry for biophysics, and we use Fable theory for passive dendritic trees, and have idealized solutions, but then I even showed you at the end that we have ways of bridging between the idealized cases and the real cases that people are now doing. I'm going to say in a moment something about the nonlinear dependence on synaptic excitation and inhibition, and I'll say a little bit in a moment about compartmental models which permit one to work with non-ideal geometry. And I'm going to show you EPSP shapes for different input locations and spatiotemporal patterns that you get with those. And I may have time to get into this discussion of electrotonic length. In fact, I already did give you this part about how you might estimate an L value for non-ideal trees. And one of the things I want to say, we've occasionally met critics and people say, oh, well, neurons don't have idealized equivalent cylinders, therefore what's it all about? Well, what we can say is that with the compartmental modeling, you don't have to assume that. With compartmental modeling, you can specify any non-uniformity of the branching structure, any non-uniformity of the membrane properties. They can all be specified, and you can explore them computer-wise. But the point is you can't get these simple analytical results. And I think historically we found that the analytical results for the simple systems were useful. They gave us insight, and I think they stimulated experiments. And so our defense now is that the simple idealized ones still give us valuable insights, but anytime somebody says, oh, well, it's not that simple, you've got to consider this complication or that complication, our answer is, sure, you can do it. You just have to specify everything. You can't make it vague, it's got to be specific. And one thing is that you can still get, if the deviations from the ideal are minor, one can get quite valuable insights from the idealized model. But if in fact you have all kinds of nonlinear channels here and there, then the only way you can deal with it is to do the complete work. Now, one other point is, if you're dealing with linear membrane, then you can actually solve the arbitrary tree algebraically. But if you're dealing with nonlinear membrane, then you really just have to do the simulation. So what I've done here is I've given things in slightly different order from what I sometimes do because I want to give some of the basics. But now I'm preparing you for the idea of the tree, the equivalent cylinder, the compartmental model. In this case, you can say that these dotted lines here, the equivalent cylinder had a length of 1 lambda. In other words, capital L is 1. And if you divide all those branches into 5 equal zones, you can also represent them as 5 compartments. Each of those then represents actually the surface area of the corresponding dendritic tree. Or for many of our computations, we actually use 10, where the compartment 1 represented the soma, and these other compartments represented different distance out in the dendritic tree. And in those compartmental computations, one assumes that that each compartment is isopotential, and that the current flows have to do with differences in potential between neighboring compartments. And so that is that approach, which I was alluding to a moment ago. And the one other thing I should mention here is that the equivalent circuit diagram that we use for quite a bit of this work was really derived from the models that Fatt and Katz originally used for at the nerve muscle junction, where we have the membrane capacity, we have a resting conductance with a resting battery, which can be some combination of potassium and sodium conductances, but one can just lump it all together and treat it as a resting conductance and a resting battery. And then you can have synaptic excitation represented by an excitatory conductance with its reversal potential and an inhibitory conductance with its reversal potential. So this is now a sort of a generalized expression that can accommodate synaptic inputs. And we can also, for convenience, we can define the intensity of a synaptic excitatory input as the ratio of this conductance to the resting conductance. So that ratio is an intensity of synaptic excitation, and this ratio here would be an intensity of synaptic inhibition in terms of the conductance. Way in at the top, I have that statement for the constraint on diameters for purpose of I think I'll take a few minutes to go, because people often wonder, well, what is this nonlinearity of synaptic inputs? What are you talking about there? And I think this was put together to try to give some specific examples. So for this model, the membrane, it's easy to express. The membrane current density can be expressed mathematically as the capacitive current, the current through this resting path, the current through this synaptic excitatory path, and of course if that conductance is zero, there won't be any, and the current through this path depending on what its value is. So that's simply a statement of these parallel paths. And now if you have a space clamp, you can say that Vm is equal to Vi minus Ve, and if you have a steady state, this current, the total current has to be equal to zero. Then you can rearrange the equation in this form, and in fact you can express it here. You can say what is the membrane depolarization, what is Vm minus Er, and it can be normalized relative to the excitatory reversal potential. So what we can do here, we're expressing a depolarization of the membrane relative to the excitatory reversal potential, and it's this ratio which can be written more simply in terms of what I just said a moment ago. You use script D for the excitatory intensity, and you use J for the inhibitory, and this minus 0.1 is chosen to be something like the fact that the potassium equilibrium potential is usually on the other side of rest from the excitatory one, and 0.1 is a reasonable kind of a number to use, as long as we're not trying to go into fine detail of what were the actual concentrations of the ions. That quantity divided by 1 plus E plus J is the expression for the depolarization. Now, the way we can get the nonlinearity, first of all, we can see that there is saturation. If the synaptic excitatory conductance gets very large, that swamps everything else, and you'll get, what have I given here? Yeah, well, the limit is 1, and since we've normalized it in this way, the limit is 1. I mean, if this is very large and this is very large, everything else is negligible, and we have a ratio of 1. So that is the limiting saturation value if you have a very large synaptic excitatory conductance. Now, if you have a very large synaptic inhibitory conductance, then the J's will dominate, and you get a value of minus 0.1. That is in which you get to the reversal potential. But those are the limiting cases, and those are the saturations which you may sometimes hear people talking about. And if you're getting up near saturation, it means an additional increment of either excitatory conductance or inhibitory conductance doesn't have much effect. Now, here are some numerical examples. Suppose this script D, the excitatory conductance ratio is 2, and there's no inhibition. What you get from this expression is 2/3, 0.67. Now, suppose you double it to 4, and you still have no inhibition. Result is 0.8, which is not twice the 2/3. So that's an example of the nonlinearity. And then the second case here, we're going to consider when we have no synaptic excitation, but we have synaptic inhibition with an intensity of 4, the value comes out here as 0.4/5, or in other words, I can't quite read it myself, but it's 0.06, I think. And then if you now combine that synaptic inhibition with the previous synaptic excitation, each of them 4, the result is expressed here, and that comes out plus 0.4. So you don't have a linear combination of the two, and in fact the synaptic inhibition has a dominating effect, but not a completely dominating effect. So the last result is half of the 0.8. The linear result would have been 0.72. This is that right?
Excuse me?
I'm not sure. Yeah.
Roger, it's not so simple for me that when you say that if the excitatory conductance increases, then the limit is 1. That means that the membrane potential will get to the E excitatory, to the excitatory.
What's called a reversal potential, yes.
And that's very reasonable for me.
Yeah.
But why is it on the opposite? When the inhibitory conductance increases, then the limit is...
Is its reversal potential.
It's
The limit will be its reversal potential, reversal potential for synaptic inhibition.
Assumed to be.
okay.
Yeah,
Okay.
right. And of course, if you have many different channels, then you have to figure, and none of them are dominating, then you have to use something like the, what's often referred to as the Goldman-Katz equation for combining several different channels and getting the effective potential you get when you have a combination. So I don't know whether it was necessary to include this or not. Was it helpful or not? It takes a little extra time, but this is an explicit example of what it is we mean by the saturation effect and what it is we mean by nonlinear effects. Now, and Rinsel and I, in those earlier papers, for most of the papers, we were considering current injection. And it was with current injection that you get all those linear superpositions and linearity properties. If instead of current injections you have synaptic conductance inputs, then they don't add linearly for this reason here. And that's why it's sometimes mathematically very convenient to use current injections, which you always have to qualify this by knowing that, in fact, if there were synaptic inputs, it could be different, unless they're very small. Yeah, now here is, I think, where I answer that question about what are the values of lambda and so on. This we're looking at our uniform passive membrane cylinder. The partial differential equation, or cable equation, is shown here, where lambda is the length constant, and it can be expressed in these two different ways. And the time constant tau is equal. You can express it as RMCM, meaning the resistance per unit length and the capacity per unit length, or you can also have it cap RMCM, which is per unit area. And here are some values that we've used often for motor neurons, where Rm may be 5,000 ohm centimeters squared. Ri can be of the order of, the value that's been used a lot is 70 ohm centimeters, and some people have evidence, at least in some cells, that maybe it's quite a bit higher. People have talked of values over 200 even. Although Bob Burke told me recently, when he's reevaluated some of his data, he says values that high won't work with his expression. One of the imponderables here is when you're actually dealing with an actual neuron and actual measurements. One thing you have to worry about is has the dendritic tree shrunken in the process of the histology and the measurements, because the value that you should use for Ri is going to be very sensitive to any changes in the shrinkage or swelling of the structure. And so that adds to the uncertainties about Ri. And the value for the membrane capacity per unit area, the general value that everybody uses is 1 microfarad per square centimeter, which is a value that Cole established that ballpark many years ago. And I think there are now some detailed, and that is assumed to be, and I think there's strong evidence, that is basically the property of the bimolecular leaflet in the membrane. All membranes have these double layer of fatty molecules, and that double layer, bilayer, is responsible for this membrane capacitance. And I think people who've done very careful measurements have values just slightly lower than this, like 0.7 or something like that. But for many of us, this is a perfectly good ballpark value. So now let's see. So here, if you have a diameter of 10 microns, you get a lambda of 1.34 microns. If you have a diameter of 1 micron, you get a lambda, and this was 0.42 microns. And the tau value implied by these values is 5 milliseconds. So now if we have a boundary value problem for the partial differential equation, and that boundary value problem is simplified by putting the zero slope or sealed end boundary condition at both ends. And the solution, using separation of variables, the solution for this partial differential equation can be a product of sine of alpha x over lambda and cosine of alpha x over lambda times e to the minus 1 plus alpha squared t over tau. Now, because of the boundary conditions here, we can set a equal to 0 because the sine doesn't satisfy the zero slope boundary conditions, so we're left only with the cosine. Then we want to, if we want to satisfy the boundary condition of both ends, so that we have what it really means is an equal periods of the cosine. We either have a pi or 2 pi period. And what that means really is that if we want the argument to be pi or 2 pi or a higher number of pi, it means that alpha, this unknown, this eigenvalue, this unknown value here, has to be equal to n pi over L. And those are the eigenvalues of the system, and those values, when they put in here, satisfy the boundary conditions, and when put in here, they satisfy the differential equation. And I'll say more about that a little bit later, but the whole system can be reduced to a system of ordered differential equations if you use a compartmental model. And I've written down here what the equations are, and the details can be looked at in this 1964 chapter in a book, The Neural Theory of Modeling. And this set of equations is really the basis for all compartmental modeling. In this case, I think, let's see, have I assumed the theory? No, in this formulation, it doesn't require that you assume equal volumes. But if you have compartments of different volumes, you have to pay close attention to what are the resistances of the compartments and what are the resistances connecting the compartments. And you'll find more detail on that in the chapter that Idan and his collaborators wrote for the following chapter in the book. But so I include this only to show that there is a connection between the two. But here, the PDE, the partial differential equation, is converted to a system of ordinary differential equations, which then are underlie the compartmental model. Yep.
About the non-linearities that I just wanted to ask about all the physical models. They ignore this non-linear effects because they
Just have add and subtract inputs, you mean?
yeah, they just add and they ignore this. Is it in the? It's something basically wrong. Seems
Yeah, I agree with
basically
you.
wrong. So
I agree with you, yes. Yes, that's true, that all of the models which simply add and subtract inputs without any consideration for this kind of nonlinearity or for consideration of different dendritic locations are wrong for those reasons. I mean, they have errors for that reason. Of course, all models have certain errors, but it's useful to be aware of where the errors lie, what's causing the errors. But this is definitely an error, and that was why I showed that before, that when you have combinations of excitation and inhibition, the errors can be quite severe. Well, now I'm coming to some results that, for that chain of 10 compartments, where the soma is compartment 1 and the compartments 2 through 10 represent the dendrites. And when I'm giving a quick lecture where I include no mathematics, but I usually jump to this slide fairly early on, because what it does is to show you sort of graphically what you can then becomes part of your intuition. What we're doing here is computing the voltage transient EPSP at the soma for synaptic inputs at different locations in the dendrites. And in particular, we have cases A, B, C, and D. Case A, the synaptic input, and the synaptic input is just for a duration of a quarter of a time constant. And well, at this moment I've forgotten what the value is. It'll be stated in the books. I think the script E was 2. I think that the synaptic input conductance was twice the resting value, but I might be wrong about it. We can check it. It's not important. It's the same in every case. That's what is important. So here we have a synaptic input conductance at these two at the proximal dendritic location. This is the computed EPSP. When we shift out to same input to a more distal location, we get a little delay, a later peak, and a smaller amplitude. But the final decay here depends on the time constant of the membrane. And you see, with more proximal ones, there's more delay, lower peak, and a later peak. So those are the predictions of the model. And of course, the exact values will depend on what you assume about the electrotronic length of the system and what you assume about the time constant. But the overall, the qualitative prediction is this, that when the input is close to the soma, you get an earlier peak, a larger amplitude, and when the input is farther from the soma, you're going to get, for the same input, you're going to get this delay and a decrement in amplitude. So then, the other question then was, and I'll add, I'm not going to give you all the details, but these kinds of predictions were tested in detail with motor neurons of cat spinal cord, and we found that we found a good correspondence between theory and experiment with regard to these shapes. In fact, we developed a plot called the shape index plot, which we could then use to compare data and experiment. Because in those days, you wouldn't know what the location of an input was. What you could do is you get a family of shapes and you compare them with different sets of input for a locus, a locus of inputs and of the shapes that you would get for different locations. So originally, we had to work in the dark, in that we didn't know what the different inputs were for the different EPSPs that were part of experimentally. But later, Redmond and Walmsley in Australia actually did some experiments where they also did the HRP identification of the inputs and were able to actually compute the locations of individual inputs and compare them with the shapes of the EPSPs that they recorded and found agreement with. So then I think you find among spinal cord physiologists a general agreement that has been verified for those neurons.
When you're talking about input, I'm not sure exactly what kind of experiment you're envisioning.
Well, in those cases that I'm talking about, they were stimulating a single afferent fiber, which then had only a few synapses on the motor neuron. And in some cases, you got a shape like this, and you could say, okay, that corresponds to a proximal location or distal location. Sometimes you got more complicated shapes, and in some cases we could say, well, those represent a combination of proximal and distal inputs. And we had a whole family of results that fitted that.
Measuring it in soma.
Yeah, right. And so some of that originally had to be by inference, but now Bob Burke has done many computations for different combinations, and we have a sort of a spectrum of shapes corresponding to different locations and different combinations of locations, which I think is pretty much general agreement. Yes?
Now, do you give importance for the distance between the input location and the soma?
Yes.
But my question is, if you give an input in a x distance, it will be a constant, and then you take a soma and you give dendrites on the other side of the soma. That means you give a current here, soma, and then other dendrites. Will it have a large influence on the peak, on the rise of the peak and on the influence?
Yeah, well, if you put it on another dendrite, you mean on the other side of the soma?
Yes.
If you put it at the same distance, the shape would be completely the same. If you put it at a different distance, then you're going to get a shape that's a combination.
But the question is, let's take a soma with one dendrite, and you give an x location and input, okay? And now you add another dendrite to the soma.
Yes.
Let's say you add two dendrites on the other side of the soma, and you give the input as before, and you ask what will be the rise in the soma itself. What will be the influence of the dendrites that you added now? Will it change the input resistance?
Well, the fact that you added these others, they superimpose pretty well. The only time when you get nonlinear thing is if you have a lot of input that is changing the local membrane voltage, local membrane conductance. But the fact that, in fact, I did some calculations there where I had inputs in different trees. One of the then they add very linearly. You have the advantage that you aren't doubling the input conductance at one location. You are having an input conductance here and an input conductance there, which means that their effects add linearly at the soma. So maybe, I don't know if that's what you were getting at, but this has in fact been done theoretically. And if they're at the same distance, they will then produce the same shape. But if they're at different distances, you're going to get a combination of the two shapes. But now, the other thing, that the point I want to make next is that, okay, we've got quite a lot of data that supports this idea. So now we can ask ourselves a different question. Say, here we have 4 locations labeled A, B, C, and D. What happens if we combine them in 2 different time sequences? In other words, suppose we have the proximal input first and then the more distal one subsequently, or suppose we reverse it. And this is easy to do computationally, and there are a few, I guess, rare experiments where one can do it, but it's much easier to do computationally, as we did do. And the result is shown here, and it's in the lower half there. Those are the 2 sequences of exactly the same inputs that I showed you before, and we get an interesting result. The point is that the depolarization that you predict at the soma is not the same in 2 cases. It's significantly different. And what we can say is that this provides a possible way of detecting movement, distinguishing a movement in one direction from a movement in the other direction. Because we're talking here, we have inputs first proximal and then distal. Here we have the input first distal and then proximal. So this sequence, first distal and then proximal, is DCBA, giving this higher peak, but with a delay. And this is the case ABCD, which is first proximal and then distal. And what you see here is you see a rapid rise, but then the successive inputs don't increase the amplitude, but they do in fact delay the fall. So what one can say is, if one is a designer, you can ask, well, what is the purpose? Each of these has a value. If our purpose is, suppose the threshold for this neuron to fire an action potential lies in between here, then we can see a functional value in each of these cases. If we want to distinguish between the one sequence and the other, then this case here gives us a detection of the one pattern as opposed to the other pattern, and fires in the one case and not in the other. But suppose we have a different purpose. Suppose our purpose is to bias a neuron sub-threshold, but close to threshold, so it's ready to fire when something other input comes in. This kind of sequence is good for that. In fact, if you had more than a sort of a temporal scattering of distal inputs going on, you could maintain a sort of a plateau of sub-threshold depolarization, which then has the neuron poised and ready to fire with a little additional input. So one doesn't want to fall into the error of saying only one of these is valuable. Each one has a value, a different value, functionally.
What is the dash line? The dash line.
The dash line. Okay, the dash line is, suppose you smear out. Suppose all the inputs are smeared over all these locations over the full period of time.
So
in other words, you wash it out. That's what you get.
It's the average?
Yeah.
Between the 2?
Well, it's just about the average between the 2, but it was actually computed by saying, let's not have this spatiotemporal pattern. Let's just say that the inputs are distributed to compartments 2 all the way to 9 over the full time period. But the total amount of input is the same. So it's just saying what happens if we wash out the pattern. Well, running out of time here. I already indicated how the well, I can show this briefly, but we won't spend much time on it. I showed you how the separation of variables approach leads to this kind of solution, and that then if we have actually there are 3 arbitrary constants, the A, the B, and the alpha. But once you apply the boundary conditions, you get the A equal to 0, and to satisfy the other boundary conditions, you actually have a condition of alpha, that alpha L over lambda has to equal n pi in order to satisfy the boundary conditions of both ends. And so what we can say is that the eigenvalues of the system are n pi over cap L. where cap L, as I said before, remember, is the actual length divided by the lambda. So that was a useful result, which we actually did do, to try to do in reverse. Now what I've got to do is point out to you, and I think maybe the next one does it, the relation of alpha to the time constants. Well, you see it up here, that 1 plus alpha squared is a factor here in the time constant expression, which means, and what you can do is represent this as t over tau n, where the tau n's, the successive tau n values are longest tau, the tau which we label tau 1, and it is simply equal to 1 plus pi over L squared. And one can rearrange that equation to solve for L. So we now have an expression for L which comes from the transient, and it's pi divided by the square root of this time constant ratio minus 1. Now, this formula is strictly correct for an equivalent cylinder, but it's been applied to many neurons, and for some neurons it works and for some it doesn't. And so that's why I emphasize it is strictly correct for the equivalent for the cylinder. And you might ask yourself, okay, what kinds of values are interesting or relevant here? And I show them here. If you have L equal to somewhere around 3 or around pi, then this ratio is 2. If L is pi over 2 or 1.5, which is the kind of value we assumed is true for many neurons, or for motor neurons, then the ratio of those two slowest time constants is 5. And then if you get to very short L value of, say, 0.75, which is a quarter of pi, you get up already a big ratio of 17.
I'm sorry. Just missing that. What is this expression exactly? That's tau over tau 1?
We're talking, it's the eigenvalues that I told you before, these eigenvalues here, give us a relationship. When n is 0, then you get tau 0, which is the resting time constant. When n is 1, you get simply pi over L, and we've gone ahead and shown that the ratio of the two slowest time constants is equal to this expression, and this expression can be solved for L. L then is related to pi and this time constant ratio, which I think before it was shown, people might never have guessed it, but in fact, it means that if you are able to take an experiment and actually measure those time constants, get their ratio, you have a way of estimating the value of L.
How would you measure those two time constants?
Well, if you have a transient, and a nice clean transient, the latest decay depends on tau 0. And if you do a semi-log plot, you actually get the slope equal to the reciprocal of tau 0. Now, if you subtract that slowest decay from the rest of the transient, you get the next slowest decay, and you can get tau 1 from the semi-log plot of the difference. And that's called peeling, an exponential decay, which is notoriously susceptible to error. And the better way is to use a really well-tested computer program to pull out these time constants, the slowest one and the next slowest one. And some people are doing it that way. But since I see my time is just about up, the final comment would be that in those neurons, and there are some, whose branching and so on really are pretty close to the equivalent cylinder constraints, one can do this and get a good estimate of L. But for other neurons where the lengths deviate in a significant way, then you don't get a direct value of L this way. You get some other length. Well, I can show you one quick thing, and then we'll leave it at that. I'll have to skip over to this diagram here. I had a hunch that it would cover everything, and it's better, I think, to do things slowly enough that people follow. But what I can say is that this is a detailed dendrogram from one tree of a motor neuron that was studied by Burke and Segev and others. And what you can see there is that these do not all end at the same length, and you get some extra L value when you compute the time constants. You get extra time constants that go, say, from in out here, and also you'll have a time constant from this sub-branch to another sub-branch. You get a whole lot of additional values, which in this physiological review 1992, we actually worked them out. If you assume uniform passive membrane, you can solve all the eigenvalues for this system with a compartmental model, in which we did, and we listed them in another figure, which in fact is your next transparency, found all the time constants and all their coefficients for this complicated tree. And when we look at all those time constants, we can find that many of those extra time constants have very small, either zero coefficients or very small coefficients, which means that they are not extractable from the transient. But there are some that can be extracted from the transient, and those are the ones that we're interested in. If in those cases where the lengths of all the different subtrees, it doesn't differ by more than plus or minus 10%, you still get a good average value for L. But if they differ by more, you get complications, which we've dealt with in some detail, but I think it's not relevant to go into it now. And for the unbranched equivalent thing, you actually do get a tall one, which is useful and realistic. But in the complicated system, I have to admit that the peeling method doesn't work very well when there's that much deviation. So I think I've used up plenty of time, and maybe I should stop and I'm willing to stay for questions.